Hello, welcome to Econometrics. In this video, we will discuss about the coefficient of determination when multiple variables are added to the model. So in our preceding video, we had seen that when a variable or individual variable z is added to the model, then we get this relationship, the coefficient of determination when we added a variable z to the model, then the coefficient of determination is equal to the coefficient of determination before adding variable z to the model plus 1 minus coefficient of determination before adding a variable multiplied by the partial correlation coefficient of dependent variable and additional variable z. Now in this video we will replicate this result, but this time we are going to add more than one variable. That is when we add multiple variables to the model. So what would this relationship look like? And we know that when we add dependent variable to the model, so the sum of the square of the residual, it decreases by this component of factors, and from the partition regression we can always calculate the beta estimate for this individual variable z by making use of this relationship. Here to this model we have added an individual variable z, and the OLS coefficient c can be calculated making use of this formula. The coefficient of determination is given by the sum of the square of the variation in dependent variable explained by the independent variable or the regression model divided by the sum of the square of the total variation in the dependent variable, and this is further equal to this relationship. From this relationship we know that, and we penalize the source of variation, we divide it by the degrees of freedom, and this is given by the adjusted R square, and we know this relationship as well. Y is equal to X1b1 plus E1, where E1 is the residual when we have independent variables contained in matrix X1. And matrix X1, the first column is the column of ones for constant, and it contains some independent variables. So this is our model, and let us take another model. Y is equal to X1, let me call it age D1 plus, and let us add to this model, let us add other independent variables represented by matrix X2, and we have beta 2 plus E1 when we add other independent variables. So these are the errors, and we know that when we add independent variables, other independent variables to the model, the residual, the sum of the square of the residual is going to decrease. Now let us generate a residual matrix for the independent variables X1, and let us pre-multiply both of these models by this M1. And for y is equal to xb plus a, if the error maker matrix, that is the residual maker matrix, then my, this would be the residual term, because when we regress y on x, this is the residual we are going to get, and mx, if we regress x on x, this would be equal to 0, and me, this would be equal to the residual term, because if we regress residual term with x, then x cannot explain anything of the residual term. Residual term is a dependent variable, should be equal to the residual term itself in this regression. So following that process, we have m1y, this would be equal to e1, because if we regress x1 on x1, then this would be equal to 0, and we are left with this term. And if we regress e1 with x1, then x1 cannot explain anything of e1, therefore this should be the residual term itself. Now let us pre-multiply this side as well. Here x1 and x2, both of them are the independent variables, and they are orthogonal to this either term e1 when we add other additional variables in matrix 2. m1y, this is our the residual term e1, because this x1 in the model and this x1 in this model, they are the same x1, so this would be equal to e1. And when we regress x1 on x1, there is no residual values, this should be equal to 0, so we are left with m1 x2 beta 2 plus, and again x1 and this error term, they are orthogonal, so the entire residual term should be this residual term itself is this x2, and this residual term e1 they are also orthogonal. That is why this relationship, they form a right angle triangle. So if we take the transpose of it, e1 transpose e1, that is the sum of the square of the residual, is the individual sum of the square of these components, that is h square is equal to p square plus b square from a right angle triangle, Pythagorean theorem. Now let us divide both the sides by this into, let me multiply here with y transpose m1y divided by y transpose m1y plus, and we have already seen that, so this should be equal to 1 minus coefficient of determination when we have x1 is the independent variable, this is equal to plus, and this is equal to 1 minus coefficient of determination when we have both matrix x1 and x2 is the independent variable, and plus 1 on the left and plus 1 on the right, they cancel out. Now let me switch the position of this r square. Let me bring this r square to the left. This is equal to, and this coefficient of determination to the right, and let me arrange a little bit. And age in this model, y is equal to x1b1 plus e1. m1y was equal to e1 only. So here m1y, this is equal to e1. Let me substitute the value actually. Plus this is again equal to 1 minus r1 square. This much is equal to 1 minus r1 square. And when y is xb plus z, see, for individual variable z plus u, we know that this c was equal to, and similarly we had seen that r asterisk square yz into y asterisk transpose y asterisk. So we are used to with this result from our previous video. If we refer to our previous video, these results are well-known results. Add the numerator, so to this part is equivalent to c square z asterisk transpose z asterisk, and this must be equal to r asterisk square yz into y asterisk transpose y asterisk. In the denominator we have y asterisk transpose y asterisk, so that cancels out, and we are left with simply r asterisk square partial correlation coefficient between the dependent variable y and independent variables contained in matrix x2 when we partial out the effect of the independent variables in matrix x1. So this is the result for multivariate, and this is for the individual variable. When individual variable z is added to the model, when multiple variables are added to the model. So this is the partial correlation coefficient of dependent variable and z after parceling out the effect of x. Here z is our individual variable, while this is the partial correlation coefficient of the dependent variable and the independent variables contained in matrix x2 after parceling out the effect of the variables contained in matrix x1. As we have already seen that as we go on adding the variables, the coefficient of determination always increases. That is why we calculate the adjusted r square. This is our general formula, and making use of adjusted r square, we compare the models and sometimes we select the models. Besides Akaiki's information criteria and Bayesian information criteria, we can use Amemiya's prediction criteria in order to compare the models. And the adjusted R square for the model J can be calculated making use of this formula. According to this method, we choose that model J which minimizes the Amemiya's prediction criterion. For example, if there are three models, that is J is equal to 1, 2, and 3, then for each model we calculate the Amemiya's prediction criterion, and we choose that model J for which the Amemiya's prediction criterion is the lowest. This is how we compare the models under Amemiya's prediction criterion. We will cover the model selection process and the methods like Akaiki information criterion and Bayesian information criteria in the future. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.